But suppose I tell you that, in a very real and precise sense, light does not move. Not the way a baseball moves, not the way a car moves, not even the way a ripple moves across water. And if that sounds like nonsense, good. That means we found something interesting. Because physics often begins exactly where common sense becomes uncomfortable. So here's the puzzle. When you see the sun, you are seeing light that left the sun 8 minutes ago. It traveled 150 million kilometers to reach you. That sounds like motion. That sounds like something crossing space over time. But from the light's own point of view, if we dare to use that phrase carefully, no time passes at all. How can something take 8 minutes to reach us and yet experience zero time? How can something move at the fastest possible speed and yet, in a deep sense, not move through time at all? To untangle that, we have to be very careful about what we mean by move. Let's start with the familiar. If I throw a ball across the room, we can describe its motion simply. At one moment it's here, a second later it's there. It covers distance as time passes. We can measure its speed as distance divided by time. Nothing mysterious. If you film it in slow motion, you see a continuous progression of positions. Movement in everyday life means changing position over time. Now imagine a train. You're sitting inside, and it's gliding smoothly along the track. You feel still relative to the seat. A person standing on the platform says you're moving at 100 kilometers per hour. Who's right? Both. Motion, as Galileo realized, is relative. There's no absolute rest, only motion compared to something else. So already we see something interesting. Movement is not a property an object carries in isolation. It depends on who is observing. Newton took this idea and formalized it. He imagined space and time as a kind of grand stage, absolute, fixed, and universal. Objects move across that stage. Time ticks the same for everyone, everywhere. Motion is relative, but time is not. For a couple hundred years, this picture worked beautifully. Then something strange happened. In the 19th century, physicists were studying electricity and magnetism. Experiments showed that light is an electromagnetic wave, oscillating electric and magnetic fields propagating through space, and Maxwell wrote down equations that predicted the speed of those waves. That speed wasn't arbitrary. It came out of the constants in the equations, and it matched the measured speed of light. Here's the odd thing. Maxwell's equations didn't say the speed of light depends on how fast the source is moving. They predicted a fixed number. Now, if light were like a baseball, this would be bizarre. If I throw a ball from a moving train, someone standing on the platform measures the ball's speed as the train's speed plus the throw speed. Speeds add. But if I shine a flashlight forward while riding a train, someone on the platform still measures the light at the same speed, 300,000 kilometers per second. Not plus the train speed, just the same speed. Experiments confirmed this again and again. The Michelson-Morley experiment famously tried to detect Earth's motion through a hypothetical ether, a medium for light waves. They expected to see light moving slightly faster in one direction than another because of Earth's motion. They saw nothing. The speed was the same in all directions. Now we're in trouble, because if the speed of light is the same for everyone, then our comfortable Newtonian picture of absolute time must be wrong. Let's do a thought experiment. Imagine a simple clock made of two mirrors facing each other with a pulse of light bouncing between them. Each bounce marks a tick. Light goes up, reflects, comes down, tick, tick. If the clock is at rest relative to you, the light just goes straight up and down. Now imagine the clock is moving sideways past you at high speed. From your perspective, the light doesn't go straight up and down anymore. It travels diagonally, tracing a zigzag path as the clock moves. And that diagonal path is longer than the straight path. But here's the catch. The speed of light must remain the same. So if the path is longer and the speed is unchanged, what must happen? The time between ticks must increase. The moving clock runs slower. This isn't philosophy. It's a direct consequence of insisting that the speed of light is constant. And experiments confirm it. Fast-moving particles created in the upper atmosphere live longer than they should. Atomic clocks flown on airplanes tick more slowly than identical clocks on the ground. Time itself stretches, so motion through space affects motion through time. Now we're ready for something deeper. In everyday thinking, we treat space and time as separate things. You move through space. Time just passes. But relativity forces us to combine them into one entity, spacetime. In spacetime, every object traces out a path called a world line, and all objects move through spacetime at the same combined speed. Let me say that carefully. Everything, you, me, planets, electrons, moves through spacetime at one fixed rate. The difference is how that motion is divided between space and time. If you're sitting still in this room, you're moving entirely through time. You're not covering spatial distance, but seconds are ticking by. If you start walking, some of your motion shifts from time into space. Your clock ticks a tiny bit slower compared to someone at rest. If you could move faster and faster through space, more of your motion would shift away from time. And at the ultimate speed, the speed of light, something extraordinary happens. All of the motion is through space. None of it is through time. From this perspective, light does not move through time at all. It doesn't age. It doesn't experience duration. For a photon, the particle of light, the moment it is emitted and the moment it is absorbed are separated by distance in space, but not by time in its own frame. Now we have to be cautious here. Strictly speaking, relativity tells us you cannot define a rest frame for a photon. The mathematics breaks down. So when we talk about the photon's perspective, we're using shorthand. It's a limit case, but the limit is revealing. As an object's speed approaches the speed of light, time dilation becomes extreme. Clocks slow, lengths contract, energy increases. At the speed of light, the time between events along the light's path shrinks to zero. So in that precise relativistic sense, light does not move through time. It connects emission and absorption in a way that collapses duration. Let's make this more vivid. Imagine a star, 1 billion light years away, emits a photon. That photon travels across expanding space for 1 billion years, eventually landing in your telescope tonight. From our perspective, it took 1 billion years. From the photon's limiting perspective, no time passed. Emission and detection are adjacent events. It's as if space-time folds in such a way that the path of light is a kind of seam-stitching distant places together without temporal separation. That's strange, but we can go further. We also know from quantum mechanics that light is not simply a little bullet traveling along a single path. In the double-slit experiment, individual photons create interference patterns as if they explore many paths simultaneously. There is a powerful way to think about this called the sum over histories. To compute the probability that light goes from point A to point B, you imagine it taking every possible path. Each path contributes a little arrow, a complex number, and when you add them all together, most cancel out. The paths near the straight line route reinforce each other. So in quantum theory, light doesn't simply travel one trajectory. It samples all possibilities, and what we observe emerges from interference. Now combine that with relativity. Light does not experience time. It follows null paths in spacetime, paths for which the spacetime interval is zero. In geometric terms, the structure of spacetime is such that light traces out the boundaries of what can influence what. These boundaries are called light cones. Every event in spacetime has a future light cone and a past light cone. Signals cannot travel outside these cones without exceeding the speed of light. So light defines the causal structure of the universe. It is not merely something that moves within spacetime, it determines the geometry of spacetime. That's an extraordinary shift in perspective. We started with a beam crossing a room. Now we see light as the thread that weaves together cause and effect across the cosmos. But let's come back to the provocative statement. Light does not move. In what sense could we mean that? Think again about ordinary motion. A car moves because at one time it occupies one location, and at a later time, another. The two events are separated in time and space. But for light, along its path, the separation in spacetime between emission and absorption has zero proper time. In relativity, the distance between two events in spacetime isn't just spatial distance minus temporal distance, it's a combination. For light, that combination equals zero. So although light traverses space in our coordinates, in spacetime geometry its path has zero length in the temporal sense. It doesn't march forward through time the way you do. You and I are always aging. Even sitting still, we move forward in time at 1 second per second. That's our inexorable motion. Light, at its limiting speed, uses up all of its motion traversing space. You might say that from the structure of spacetime itself, light is frozen in time. Now here's another twist. If you try to accelerate a massive object to the speed of light, you run into trouble. As its speed increases, its relativistic energy grows without bound. To reach light speed would require infinite energy. That's not a technical inconvenience. It's a deep feature of space-time geometry. Massive objects always have some motion through time. They can never convert all of it into motion through space. Light, having zero rest mass, is born at that limit. So light does not accelerate up to its speed. It is created moving at that speed. and it never slows down in vacuum. There is no rest state for light. Think about that. You can stop a ball, you can slow a car, but you cannot catch up to a photon and ride alongside it. The equations refuse to allow such a frame. It's as if light exists only as a relationship between events, not as an object lingering in time. Now let's complicate the story because nature always does. In materials, glass, water, air, light appears to slow down. Its speed becomes less than c. Does that mean light is violating its own rule? Not quite. What's happening is more subtle. Light interacts with the charged particles in the material. The electromagnetic wave induces oscillations in the atoms. Those oscillations re-radiate light. The overall effect is that the wave's progress through the material is delayed. But between interactions, the fundamental propagation speed in vacuum remains c. The apparent slowing is an emergent phenomenon of interaction, not a change in the underlying rule. So the invariant speed of light in vacuum remains untouched. Let's step back and ask a different question. Why should there be a maximum speed at all? Why can't signals propagate infinitely fast? If they could, cause and effect would unravel. In some frames of reference, effects would precede causes. You could send a message into your own past. The existence of a finite maximum speed preserves causal order across different observers. Light speed is not just a property of electromagnetism. It is the conversion factor between space and time. In relativity equations, c appears not merely as a speed, but as the bridge linking meters and seconds. If you measure time in units of distance by multiplying by c, space and time become two aspects of the same entity. So when we say light does not move, we are really confronting the idea that motion itself is woven into space-time geometry. Light doesn't crawl through a pre-existing arena of time the way a beetle crawls across a table. Light traces the structure of the arena. Now here's something even more intriguing. When we look at distant galaxies, we see light that has been traveling for billions of years. The universe has expanded during that time. Space itself has stretched. Does light move through expanding space, or is it carried along with it? The answer depends on how you describe it. In cosmology, we often say space expands and light rides along, its wavelength stretched, redshifted by the expansion. But locally, in small regions, the speed remains c. So again, light is not simply a traveler crossing a fixed stage. The stage itself evolves. The deeper we look, the less satisfying the ordinary idea of motion becomes. And there's one more layer. In quantum field theory, light is not fundamentally a little particle zipping along. It is an excitation of the electromagnetic field. The field exists everywhere. When it vibrates in a certain way, we detect a photon. So perhaps we should say that light does not move as a tiny marble moves. Rather, the electromagnetic field oscillates, and the pattern of oscillation propagates. Think of a stadium wave. The fans don't run around the stadium. Each person stands up and sits down. The pattern moves. The individuals mostly stay put. Similarly, in a wave on a string, the string itself doesn't travel down its length. The disturbance propagates. But even this analogy has limits, because in quantum theory, the distinction between particle and wave blurs. Still, the key idea remains. What moves is not a little object carrying its own private clock. What propagates is a disturbance constrained by space-time geometry. And that disturbance, at its fundamental level, follows paths of zero proper time. So when someone says light moves at 300,000 kilometers per second, that's true in our coordinate system. But when we ask how light experiences its journey, we find that the question dissolves. Light does not have a rest frame. It does not age. It does not tick. It links events across space without traversing time. And here's the philosophical sting. We experience the world as unfolding in time. Past to future, cause then effect, waiting, aging, becoming, but light, which makes sight possible, which carries information from the universe to our eyes, operates outside that temporal flow in the relativistic sense. It is as if the messenger connecting the cosmos is timeless. Now, does that mean light is magical? No, it means our intuitive categories, moving objects, flowing time, are approximations that work at low speeds. When we push them to the limit, they bend. And that bending reveals structure. So let's return to the beginning. You flip the switch. The room fills with light. In your coordinates, the light traveled across the room in a tiny fraction of a microsecond. But in the geometry of space-time, the emission at the filament and the absorption at the wall are connected by a path of zero proper time. The light does not live through the interval the way you do. It simply relates one event to another, and perhaps that's the deeper lesson. Motion is not absolute. Time is not universal. Light is not just something that moves. It is the boundary between what can and cannot influence you. It is the ruler by which space-time measures itself. So in a poetic but precise sense, light does not move. It defines movement. It does not age. It defines time. And the next time you look at a star, remember, the photon reaching your eye may have traveled for billions of years by our clocks. But along its path in the deep geometry of the universe, there was no ticking at all, just a connection across the vastness. And that is far stranger and far more beautiful than simply saying it moved.